A warm welcome. Today we are in conversation with one of the leading minds in theoretical physics, Professor Ashoke Sen. He has made profound contributions to our understanding of string theory and fundamental physics and has been recognized with several of the highest honors, including the Breakthrough Prize in Fundamental Physics, the Dirac Medal, the Shanti Swarup Bhatnagar Award, the Padma Shri and the Padma Bhushan. We are delighted to have you with us today, Professor
Thank you very
Sen.
much.
Welcome. I'd like to begin by asking, in areas like theoretical physics, especially string theory, mathematical formalism is very crucial. So,
Yes.
at a conceptual level, how do you think of a problem before formalizing it?
I think it is formulated as one is doing research. At least maybe different people have different ways of doing research. For me, the problem gets formulated while doing research because you start exploring various things, see where you can make progress, what kind of techniques may be useful,
Yes.
and then you use them. Maybe you get stuck. Again, you try to look for ways. So, it's not that there is a systematic procedure that you follow, right, which maybe in experiments you have to do it more systematically. In theory, I think mostly it happens by random walk, I would say.
Right. And what kind of math would be useful when you try to, especially when you have to deal with string theory, theoretical physics? What is the math that you use the most?
I think that again depends on the kind of problem you are working on, right. Some people use very little maths, right, they can make a lot of progress using physical insights.
Yes.
But then some people are highly mathematical, they use work on more mathematical aspects of string theory. So, for example, number theory, algebraic geometry, these are the two things that are very often used in string theory, but topology plays an important role.
Yes.
So, I think again all kinds of mathematics is used, right. It's just a question of what kind of problem you are tackling, because string theory is a vast subject and there are
Right.
many different kinds of problems.
Yes, and in that context, your work on S-duality basically shaped how physicists think about the different kinds of string theory. So, what is the intuition behind the idea that all string theories are in fact the same?
Yeah, the point is when string theory was first formulated, it was formulated what people call in perturbation theory. You have some parameters which you take to be small, and then you can study the theory well for small values of the parameter. And from that perspective, different string theories look very different.
Yes.
But it's only when you start exploring what happens when the parameter becomes large, then you find that it becomes it goes into a different version of string theory. Again, I would say that this is it's not that you can systematically arrive at these kinds of conclusions. You start studying various things, maybe a little thing you can study better than other things, and that little thing you use to compare between different string theories to see if you can see some connection.
Yes. Yes. And so, why is a unified theory important?
One point, okay, there are different ways of thinking of what is unified theory. One is that you want to unify all forces.
Yes.
Now, what one means by unifying all forces is that there should be a single theory which incorporates all forces. Okay. It's not that, so it's not more than that, right? It need not be that there is same kind of technique that you use for studying all forces, but there should be at least one theory which should be able to contain all the forces. Because if we think of a particle like electron, right, it has various kinds of forces. It has electromagnetic force, it has weak force,
Yes.
and it also has gravity. So, if you have a theory of gravity that is separate from a theory of electric force or a theory of weak force, then how do you explain the property of an electron?
Right.
Because electron has all kinds of forces, right. So that's the sense. It's not that our universe is disconnected, is divided into two parts. One part has one kind of forces and another part has another kind of forces, because then they will never talk to each other, right. This is not the way nature works.
Right.
So that's the reason why you want to have a unified description,
Right. And
of all
ultimately
forces.
understand all of nature.
Exactly.
Yes. So, what exactly is string theory trying to achieve in all of this? I mean, is there still a lot that it can achieve?
Yeah, I think there is still a lot to be achieved. the main goal of string theory is to find a theory that incorporates all forces of nature and explains all elementary particles that we see in nature. So, in a sense, this is the basic formulation of how nature works.
Yes.
Right? Doesn't mean that even if string theory is completely successful, doesn't mean that you have solved all problems in nature, because it's like using string theory, you will probably not get much better idea of how atoms form molecules or how molecules form life, right?
Yes.
Because for that you need to use different kinds of techniques.
Exactly.
But it's just an attempt to find a single description of the most fundamental building blocks of nature.
Right. So, do you think we teach sufficient science and math at the school level for students to develop curiosity and, ask difficult questions as they move on, or relevant, interesting questions as they grow older?
Yeah, I think we certainly teach a lot, right? Whether that is the best way to, make them curious is not quite clear,
Yes.
because the way we teach is not
Is also important.
Yeah, is also important, right? It's you don't teach them to be curious, right? To teach them more to pass exams and get
Yes.
good marks.
Yes.
Right? So I don't think the problem is with how much we teach.
It's the way we do.
The way we teach.
Right, exactly. So, can you tell us what it was like for you, how your thinking developed as you were in school and then a bachelor student at Presidency, master student at IITK, and finally a PhD at Stony Brook. So, through that journey, how did your thinking slowly develop into what it is today?
Yeah, for me, I think it was a very slow process. In school, I was interested in maths. I was also vaguely interested in science. Science was a glamour subject at that time, so I thought I want to be a scientist, even though I had no idea what science was about.
Yes.
Right, and then in college again, I got to know a bit more about what physics is, because there I took physics honors, and I had very good classmates who are all interested in physics. So that way, I think that
I think
stimulated.
peers are as important.
Yeah,
as
peers
teachers.
are certainly as important.
Yes.
We had also very good teachers
Yes.
who taught us. And then in Kanpur, it was a different kind of atmosphere, but again, I think there are very good teachers, and we learned. And then I went for my PhD in Stony Brook, and that's where I got into the subject that the quantum field theory, the particle physics. And
yes,
yeah, so I think for me it was very gradual. It was not that there is one stage where somehow I had the idea that I will become a scientist.
Yes.
Right, this has been there even from school.
Yes.
Without knowing what science is about.
There was no sudden change. Or
yeah, and it was not even that I knew very much about science. I had an older cousin who sometimes used to bring me books in popular science, which I used to read. But that was all my curiosities about science at that time.
Yes, of course. And I think also, nowadays for students to have access to books, especially in rural areas, makes it's harder. Also in the language that they speak, so all that would really help get them to that curiosity, right?
And I think another thing which helped was that we had some heroes, because there are local heroes like S.N. Bose, everybody knew, right? Not just students, but a common person would know the name of S.N. Bose and M.N. Saha, and that certainly probably helped.
Yes, exactly. Someone to look up to.
Yeah.
So, do you think good research is driven more by exceptional insight or by sustained effort over time?
Sustained effort certainly is more important, right? But insight is also important, right? So I think it's a combination of both. But without sustained effort, I think it is very hard to get anywhere, because even insights really come from sustained effort.
That's true,
right? Because you start thinking about a problem again and again and again, and you get insight suddenly, right, from where you don't know, but
it has to burn
exactly.
you.
Yeah,
and
suddenly it clicks.
Yes, exactly. Right. So, what do you think a student should focus on as an undergraduate if they want to pursue research in theoretical physics or physics in general?
I think one thing that students should learn, of course they should learn some concrete things, but what is most important, I think, is that you should be able to distinguish between what you know and what you don't know. because sometimes I have seen students think that they know a lot, right? Maybe they have seen some vague outline of the subject,
Yes.
right? And they feel that they already know the subject, right? Where they really don't know. So I think this is probably the most important aspect of learning, that if you know what you don't know, then you will learn, right?
Right.
Because then you will put the effort.
Right. And also, if you know what you don't know, then you know what you have to learn.
Exactly. Then you know what
Yeah.
you know what you have to learn.
Yes.
The second point I would say, this is for research, is that most of research, at least in theoretical physics, maybe also in mathematics, I don't know,
Yes.
is most of the time you spend not doing anything because you are stuck at your problem.
Right.
When things move, it moves fast, right? But then you are again stuck, and for months nothing happens. Right? And somehow they have to learn how to cope with it, right?
Yes.
Particularly for good students, what happens is that all their life they have succeeded without putting too much effort, and then this can really upset them.
Yes.
Right? And I think to be able to deal with this situation is the again a very important
What
aspect
is
of
your
doing
advice
research.
to them on how to deal with this?
I think it's a personal choice. For me, for example, it helps when I'm stuck, just take a completely different paper and start reading, right? Even though it has nothing to do with my research,
Yes.
right? You learn something new that way, and sometimes somehow while reading that paper, it clicks, right? Where you are stuck, maybe something gets unstuck. But for others, it may be different,
Yes.
right? I think it's everybody has to discover on their own what is it that.
I think in a research institute, one can attend seminars also.
Exactly, you can attend seminars.
Right.
You can just generally talk to students, right?
Right.
Ask, see what other people are doing.
Yes.
Yeah.
Right. Okay. Um,
Or
So-
even just hang around, right? In the
yes.
cafes, right?
Yeah,
that
of course.
can also help.
I
right?
think in most academic institutes, a lot of discoveries happen over a cup of
Exactly.
tea or coffee.
Yeah.
Right.
Yeah.
Right. And even some of the best discussions happen in the
Yeah.
canteen.
Exactly.
Okay. So, what I mean, through your journey as a physicist, how have you seen physics research change over your career? Um, what were the problems people were focusing on? How has that changed, if at all?
In my field, the central problem remains. There has been a lot of progress, right? But still, we don't know how string theory eventually makes connection with nature, and that's certainly a central problem.
Yes.
But as that central theme is pushed, I think it has branched in many different areas, right? There are many new kinds of developments that have come out of string theory, right? Like even studying quantum field theory using string theory has become a big subject. Then something what people call scattering amplitude, studying that also has become a big subject. So there, I think it has branched in many different ways. Also, I think the computationally, it has changed a lot.
Yes.
Right now, computers are part of life.
Yes. And
And
AI.
AI, yeah.
Yes.
In fact, a lot of the work now is being done using AI.
Yes.
So that way, things certainly have changed a lot.
And I think more and more authors are using AI as co-authors, right?
That's right. Yeah.
Sometimes AI is used to author a research paper itself.
Exactly.
So,
Yeah.
what is your take on that? Have you ever, used AI recently while doing any of your research work?
Yeah, I have used AI certainly.
Yes.
Not maybe for not as a co-author, but
Yes.
certainly,
For a computer
whenever I
science.
need, I have a question,
Yes.
I can put in AI, right? Or for example, if you have written some paper and you want to see if you have missed out something, or if you want to see how the referees might react, you ask the AI to refer it,
Okay.
right? So that way AI can be very useful,
Yes.
because it will give a broad overview, right? Not that, AIs of course make mistakes all the time,
Yes.
right? Sometimes it will put pi in the numerator instead of in the denominator, so that those things can happen.
Yes.
But my feeling is that if you know certain things, AI is very useful, but you cannot trust AI on a completely new subject.
Yes.
Right? You have to be able to judge whether what AI is saying is correct or not.
Yes.
And it's true in all aspects, in research, in as I said, opinion on papers, right? So you have to be very careful, right? Maybe that will change in the future,
Yes.
but otherwise AI is a very useful tool.
Right. Okay. So, if a new institute were to start an undergraduate program in the basic sciences, now, first of all, I mean, basic sciences are already something which most students do not run after anymore, right? That's not the first choice. So, if a new institute was to start a course today, an undergraduate, what principles should it use in its design, right? Both in terms of curriculum and the way students are taught. Um, what do you think?
Yeah, I would say perhaps, I mean, if it's more curiosity driven, right? I mean, you try to make the students think more,
Mm.
right? Rather than just putting them through lots of courses, right? I think that can certainly help. I mean, that will be different from the way things are taught normally, right? Where people come and teach a lot, and then the students have to mug up what they have learned.
Yes, and then vomit it in the exam and
Exactly.
forget
Yeah.
about it.
Yeah. So I think if one wants to make a difference, one could try to make teaching more innovative, right? Where students actually participate a lot in the course, not just as passive listeners.
Yes, and I think a huge part in that is also the number of students in a class, right? When
That
it's a
is true.
smaller
Yeah.
class,
Yeah.
it's much easier
Yeah.
to do
So I think
something
you
like
have to
this.
have, I mean, you cannot have too many students in a class,
Yes,
right?
yes,
So that way, smaller universities will have an advantage that if you have less number of students, you can actually be a lot more innovative.
right. And finally, what advice would you give to a student who's interested in science but unsure if they are good enough to pursue science?
I would say that you should try, right? Many people I know have got their PhD and then moved on to something else. Particularly now, it's easier than what it was in our time.
Mhm.
In our time, if you have done a PhD in physics in India, it was very hard to move anywhere to anything else. But now, software companies or AI, for example, I mean, AI companies, they are hiring lots of scientists,
Yes.
right? In fact, most of their employees are probably scientists. So that way, I would say that you try it and then you decide, right? After you get a PhD, you always have a choice of moving on to something else.
Yes. Okay, so that was a conversation with Professor Ashok. Thank you so
Thank you very
much, sir.
much. Thank you.
Right.